millimeters. And the idea is to find all 6 stress components. We have to do a little bit of Sherlock Holmes deduction here to decide what kind of an element this is. But if it's a 4-noded quadrilateral in 2 dimensions, it would be logical to have a so-called bilinear set of displacement functions. These would be linear if you take any cut parallel to any of the 2 coordinate axes. So this matches up then, giving us the 4 degrees of freedom in terms of either the generalized coordinates or the nodal coordinates. Let's talk some more about this displacement field. We've been given that the outward displacement field is a constant U value, 0.001 millimeters over the face of the ring element. And then that the contraction in the W direction is a uniform contraction toward the middle. So you could set up a simple little polynomial displacement field here. It would give us our W displacement. Now, you can actually do this formally if you'd like by matching the nodal displacements to the internal field. So it could be done in a typical shape function manner or a displacement function manner. The strain displacement law is the general one for axisymmetry, and now we know what the entry displacements are here in order to calculate what the strains are over there. We operate on the displacement field with that strain displacement operator to get the strains. And after we do that, we find there is 0 radial strain and there's 0 shear strain in that plane. The Z component of strain is constant, but the hoop strain is not constant. It shows the inverse relation with the radius. So as you get out farther, there's a larger arc length around to close that hoop, and the outward displacement gives relatively less hoop strain as you move outward on the element. Then we go to the stress-strain law, and as we've mentioned before, that's the same law at a point as the plane strain law is. And here we solve for our stresses in terms of our known strains over here. We can now multiply out and get the stresses. The stresses on the left here are equal to these material constants, and then we have the 4 components in here. There's no shear stress, but there are stresses in the other 3 components, and none of them are constant. Of course, the hoop strain wasn't constant, but now we get none of the radial, the hoop, nor the Z stress to be constant. So in each case, we've got a stress that has a constant part and then a part that diminishes with the radius. Well, that completes our solution for the stress and strain throughout the element.